Okay, I think we can start. If you ever decide to go to conference and give a talk for the first time in your life, I think this is the perfect slot. Last day of the conference, right after the lunch break. All right, so any developers here? All right, then we can get maybe a bit more technical. What I try to prepare is mixed content, so I intend to mix technical aspects, also some theory of the systems, which I think can be beneficial to you as a developer, because we're trying to raise the level of what we do. So today I'm going to talk about my favorite technique when building software systems, CQRS. This is I use most of the time, but before I use it at the start of the project, I always try to turn off the autopilot. I don't want for all my projects to look the same, to be structured in the same manner, because not every two projects are the same. So since this is a conference about agility, this is one of the components of being agile. Observe, adapt, and act differently based on the domain that you're building. And I think we should all be doing it. And unfortunately, we don't have too many Scrum Masters here, because when you think about what Scrum Masters are doing, and if you think about Scrum as a methodology, you will realize that Scrum itself, although trying to achieve agile results, it's not agile itself. When you look at the typical project you do with Scrum, you have usually 2 weeks sprint iterations, you have retrospective, you have planning, and this is ongoing and ongoing. People are not experimenting. Let's try to have daily stand-up every second day or something like that. Also, today I'm going to talk about, I'll try to answer the famous question, do developers really love changes? And you will see by the end of this talk why developers actually do love changes. I'll try to convince you that you should be reading ancient books, and when I say ancient in this industry, ancient is like 20 or 30, 35s ago. We'll learn, hopefully, how to recognize a Sith from Star Wars. And hopefully, in the end, I'll try to answer the question, how many databases we actually need. So first, what is our job as developers? You would say right away that this is building systems. But if you look at the life cycle of a typical project, you will realize that, no, we are not building, we are actually changing things. If you take any serious enterprise grade level project, you will realize that you're actually building something for 6 months or 9 months or a year. You launch it into production, and then what you do for the next 5, 6 years, if you're in a product company, or what people you deliver project will continue to do, they will keep changing it. So actually, if we took a hypothetical project that lasts for 10 years, 10% of the time you will spend building things. Then you will deliver it, and then you and your team will change it for another 9 years. This means that only 10% of your time is spent building, 90% in such hypothetical project is spent changing. And even today, if you think about really, really old systems that we are using, like Visa, transaction processing, or actual core systems for the banks and similar systems, you will see that actual cost of building is just a fraction. The majority of the cost is cost of a change. And we all know that change is hard. We all know it's hard, and I myself remember getting very simple change request and getting very angry, because I know immediately that I will spend some heavy time changing it. So this is what we are doing. We are changing things. What we are building is a system. So we are building systems. And actually, it's worth looking into what the essence of the system is. And now comes a bit of what I said, theory of systems curriculum. So what is a system? System is a whole composed of parts. And when you think, we use systems every day. So let's imagine a car. Car is composed of many parts. All of them are working together. So parts of the car are affecting properties and behavior of the car. And furthermore, when you think about what car is actually doing, car is giving us some behavior, so we can transport ourselves from point A to point B. And when you think about it, there's not a single component of the car that can do the same. So when you think about it, engine itself, engine cannot even transport itself from point A to point B. Wheels without a motor cannot transport themselves from point A to point B, not even themselves. So essentially, parts are interdependent. They rely on each other. And only all those parts can produce final effect, additional value that system is given us. So again, when you think about it, if you divide system into parts, you are losing essential properties of the system. And there are some interesting consequences or implications of that. So we can conclude the system properties are new properties which are not exposed by any part of the system. And when you take system apart, you lose this additional functionality that system itself is giving. So system is not just pure sum of its part, it's something new, something additional on top of functionality of each part. And furthermore now, if you think about system analysis, if you take a card, let's imagine you split it into parts and you try to analyze it. So let's say someone hands you over a machine you never saw. How you will analyze it? There's something called reductionism. Reductionism is an attempt to split system into parts, to analyze parts, and to make conclusion about the whole system. And now, looking at this, you will understand that this cannot give you the final answer what system is doing. It would be the same as if you take a human organism, dissect it into parts, and try to conclude, for example, what is the source of consciousness. That's what reductionism is, attempt to dissolve the system. So you obviously will lose essence of the system. And if you think about optimizations, you can also conclude that if you try to optimize any single component and to expect for the system performance or system behavior to benefit from it, you can clearly see that you will fail. And if you're familiar with theory of constraints, you will see that it is practically matching. So to optimize any system, you need to take holistic approach. And when you think about term holistic, it means taking system as a whole, looking at the system as a whole. And furthermore, you will see, for example, in medicine, that the same approach is now a trend. You will not observe individual organs as a specialist. In medicine, you should, and hopefully you will, look at the whole system. So when we're speaking about the systems, we should try to analyze them, somehow make conclusions, and see where problems are. What you can see in this slide is Kuhneven framework invented by Dave Snowden in 1999. So we are going some quarter of a century back in the history. And this is mechanism invented for managers, so that managers are able to categorize systems, make some conclusions about them, and then be able to improve them. And we can apply this to the software systems that we are building. So starting from the very simplest category of a system is systems which are obvious. These systems are very, very simple. This would be a one-weekend project that you would like to build. This is, practically speaking, throwaway project. In most of the cases, you will build something simple, you will use it once, or you will use occasionally, and that's it. This is not the space where we, in our workplace, or in our, let's say you have a hobby project which you are building over the months and years, this is usually not where you spend most of your time. You will be spending most of your time as systems which are complicated. So in obvious systems, you have direct cause and effect relationship. You have a low number of variables, low number of information bits and pieces. And this is practically something, when you hear about best practices, this is where you can apply best practices right away and you can benefit from them because rules are very simple. However, what we are building in our workplaces are systems which are complicated. You remember Facebook had status, it's complicated. Usually we're not thinking about the difference between complicated and complex. So what is complicated? Complicated is level of domain experts. Let's say you need to build a system which is doing e-commerce or system which is doing text processing. You'll go and talk to experts before you know how to implement the system. In these systems, you don't have direct linear connection between the cause and effect. These systems, when we are speaking about the domain, this is opposite of easy. This is hard. You need domain expert. You'll talk to the domain experts, try to establish connections between the cause and effect, and then you will try to implement this. You have a large number of information, large number of variables which are affecting your system, and this is not area of best practices anymore. This is where you attempt or you try to implement design patterns, some good practices, in an attempt to implement this system. If we continue with systems which are problematic, finally we will reach chaotic systems, but hopefully none of us will reach that point. Hopefully, we will never go beyond complex systems. And complicated systems were opposite of easy. These systems are opposite of simple. You cannot extract rules clearly anymore. There's unmanageable, and I emphasize this word, unmanageable, tangled web of cause and effect. In these systems, you actually probe system, you observe the effect, you try to discover what is going on. Now, when you look at software systems, these would be legacy old systems, let's say without unit tests, you inherited this, you arrive at the project, and you are now trying to investigate this, what is going on. It's not clear. So both complicated and complex systems are not simple, not easy. They contain dose of complexity. And to analyze complexity, I'm reaching to 1986, ancient history in our profession. Fred Book's famous paper, go and read it, find it and read it. It's called No Silver Bullet. Fred Brooks attempted to analyze complexity and reached conclusion that complexity of the project is usually composed of two types of complexity. First one is essential complexity. Essential complexity is complexity of the domain you're implementing, and you cannot simplify this. So if you're building an e-commerce system, you have clear requirements. You know what you need to implement. That was requested from you. So you as a software engineer, you cannot affect essential complexity. What you can affect and what you will, unfortunately, more or less produce while implementing this system is so-called accidental complexity. So while essential complexity is complexity of domain, accidental complexity is complexity of your implementation. And when you think about the project you're working on, you will always be somewhere between complicated and complex. In ideal case, your implementation will be very close to complicated system. You need to make a complicated system because domain is complicated, but additional complexity of the implementation will be low. So you and your project will be positioned somewhere very close to the complicated circle. The more time passes, the more changes you make, the more hacks and patches you apply to your system, you will be pushing your project towards complex until you reach the point where system is so complex that sometimes you contemplate writing everything from the scratch. And if you now imagine how expensive change is, that you want to go and write everything from the scratch, sometimes you even get a budget from it. So this is actual problem that we are solving. Minimizing accidental complexity so that, and you remember what I said about a complex systems are unmanageable, so we are trying to build systems which will be manageable. That's our goal. And when speaking about the systems, we should go and look at one of the most ancient systems, and I'm using the word ancient obviously too much today, one of the most ancient and established formal systems that we are aware of, and that would be mathematics. When you look at functions in mathematics, and of course what we are implementing are programming language functions, you will spot some obvious properties of these functions that you're completely okay with. So we learned this in the first or second grade, some of these things. So looking at very simple function, square root. Now let's imagine I call it with number 25. I will get 5 as a result. And I can call square root of 25 150 times. Every single time I will get the same result. When I'm calling square root of 25 or square root of a, do I expect after application of this function for a to change? No, a will not change. B will also not be changed. If I have square root of a and then square root of b, I can call them in reverse order. So square root of b and followed by square root of a, I will get the same results. And wherever I have square root of 25, I can replace that with number 5. And of course, this is completely expected and natural from mathematics. But what I just presented to you is a set of good properties. So mathematical functions have these good properties. They are lacking side effects. So what is the side effect? Side effect is the additional unwanted, in most cases, unwanted functionality of the functions that we are calling. So in mathematics, you are lacking side effects. You have immutability of variables. As I said, if you take square root of a itself will not change. Mathematical functions are deterministic, which means that their final result of the computation is completely mandated by the input parameters. So every time I call function with number 25, every time I will get the same result. Mathematical functions are pure because they have no side effects and they are deterministic. And pure functions are very easy to reason about. When you think about the programming, pure functions are also very easy to test, but we will see that a bit later on. And also in programming we have, and compilers, we have concept of inlining. Inlining is possible whenever you have something that's called referential transparency. And this means that every call of the function can be replaced by the computed value of this function. This is referential integrity. And these rules are actually what makes mathematics less complex. So our life is easier, our reasoning is easier. On the other hand, when you think about what we do every day, our functions, our methods can have side effects. They can be non-deterministic, and most of the times they are, because they are reading from some kind of environment. So if my function is reading from the environment, this means almost like I have additional hidden input parameter. Or if I'm reading from the database, again, this is almost like implicit additional parameter that my function or method has, but I'm not thinking about this as another parameter. So most of our methods are impure. They are reading and writing from the environment. They are not deterministic. They have side effects. Of course, not all side effects are bad. Side effect is outputting things on the screen or sending emails, reading from the database or writing to the database. It's not that we want complete absence of side effects. It's only that we don't want unintentional side effects from our methods. And of course, methods which are not pure are lacking referential transparency, which means that reasoning about methods is hard. In other words, functions in most of the cases are not isolated. When I say isolated, I'm speaking about the interaction, reading and writing to any kind of external system or environment. And as a consequence of that, here is just a short list of things about our software which are not so good. We have systems which are less predictable because you have additional parameters coming from the environment, coming from the database, from external systems. It's harder to reason about the functions. Remember last time when you attempted to comprehend what the method is doing, or when your colleague is calling you, okay, I have a problem here, can you help? You had to sit and think about, so high cognitive load. It's hard to test. So if method is not isolated, it's not depending just on the input parameters, it's hard to test. Reusability of such methods is rather low. You cannot just extract, copy, and paste a method to another project. So we are building libraries, and this is a special endeavor where you have to respect certain premises. But when you think about it, if you have a mathematical function, reusing that is quite trivial. Have you ever tried writing a system which is concurrent? When I was at the university, we were learning about locks and semaphores and blocking, and when you actually try to implement modern high-performance system with such primitives, you will see what you will run into. You will run into local Serbian domestic service for selling tickets, where you enter to buy a ticket, and then it says you're, 15,000th in the line waiting for it. So concurrency is very hard. And when you have systems which are contained on mostly impure functions, this is where real problem is, because you cannot rely on the fact that the piece of memory that your function is using will not be changed by some other piece of the code. Or if you pass parameter to a method, can you rely on the fact that the method will not change the parameter, because you essentially are sending pointer to the chunk of the memory? So your variables are not immutable. You're losing very good properties. Composition of functions is hard. Order of calling them does matter. So that's one more problem. You change the order of calling things and you end up in unpredictable places. Refactoring is also harder. Debugging, I don't want to even talk about that. You have something that's called dishonesty. Anyone knows what honest methods are? Honest methods, if I remember correctly, are those methods which in their signature are telling you everything you need to know. So if I have a method which is accepting certain parameters, returning return value, that's everything that method will do. You remember how Java has throwing exception declaration as a part of the method signature. That's the whole idea, for you to get complete information what method is doing just by looking at the signature. But if you have side effects, your method is dishonest, it's lying to you, you need to go and examine it if you have implementation to discover what it is actually doing. Portability is also problematic because, again, taking piece of the code or taking method or function and porting it to other project becomes a bit harder. And again, if you think about everyday practice, when was the last time when you took a chunk of code from another project and brought it to the current project that you're using? And finally, idempotency. If you're building distributed systems, you are probably aware there's no such thing as exact once delivery. This is a lie. In most distributed systems, you can count on at least once delivery, which means that sometimes you will execute same function more than once. Idempotency is the property of the function that guarantees that no matter how many times you execute a function or a method, final state of the system will be the same. So if I send command, add this product to a shopping cart, if I don't get response, if I send again, add this product to a shopping cart, I shouldn't end up with 2 items in the shopping cart, I should end up with 1. This is idempotency. This is essential property in building distributed systems. And this is one more thing you're losing with impure functions. And overall, when you look at what was the first structure after you left university or high school or course, when you started working, it was something like this. This is called stereotypical architecture. This is what lots of teams are using because it's easy, simple. If you have junior colleague or entry-level developer, this developer will also be familiar with it. So you have a client. Client is sending commands, requests, queries to the system. System is accepting them. Then you have a modification of domain objects, and these domain objects are being stored inside of the database. And then you have some kind of DTOs, or some people call them view models. You send the query to your system, system computes, populates, return, you show it on the screen. So this is architecture of a typical CRUD application, and of course there's nothing wrong with it if you're building small, simple application. However, over time, people building big systems and people building many systems concluded that there's an approach that's making their life easier. In this slide, you can see, again, ancient book. One of the heaviest books you can find in the market. It's over 1,300 pages big or large, whatever word you want to use. And the author is Bertram Meyer, who's inventor of Eiffel programming language. If you need to read one book about object-oriented programming, I think this is a good candidate. And you will realize that almost everything that is to know and to learn about object-oriented programming is contained here. And it's a bit strange when you think about it that a couple of decades ago we got almost everything we need to know about object-oriented systems. So on page 751 in chapter 23 of this book, you have CQRS introduced. What is also interesting is that this was the first book where I ran into notion of craftsman, so software craftsman, software crafting. And in this book also author introduced notion that class design is actually interface design. When you think about the public interface of the class, this is precisely that, kind of the contract that is promising you. So if you send something, if you call some methods of a class with some arguments, you will get some things back. So you can look at it as a contract. So CQS was introduced here as a practice that was spotted to be effective. CQS is essentially not architectural pattern, it's a principle. And I'm emphasizing the word principle, and you will see a bit later on why. So CQS is Command Query Separation Principle. So word separation essentially means putting things apart, setting things apart. And this principle states that all your interactions with software systems should be divided into two categories. It should be either command that you are sending to a system, requesting system to change, but you will not get back any response. Or this could be query that you are sending, you're requesting state of the system, you will get back state, but without changing the system. Essentially, whole CQS can be summarized into sentence that, or statement that asking the question should not change the answer. In other words, now when we go back to the side effects we talked about, queries are not producing side effects. So you are left just with commands which are producing side effects in the sense that they are changing some state of the system. And CQS is, unfortunately, a bit misunderstood in the sense that people are taking this as a dogma. And now we go back to the question from the first slide, how to recognize a Sith. So Siths are characters which are thinking in absolutes. An absolute would be always and never. And then people go and say, okay, I'm applying CQS. Everything must be either command or a query. But what we are doing here, we're actually building software. We are solving the systems. We are developing systems to solve a problem. CQS is not our end goal. CQS is just the means of structuring your application on the surface to be more manageable. And typical question you can find on Stack Overflow and all over the internet is, question, if I create new entity in the database, can my CQS-based system return back ID from the database? Of course it can. So we shouldn't be dogmatic, we should be pragmatic. When it makes sense, it's not a problem. If your system is 90% or 95% CQS compliant, this is great. It doesn't have to be 100% compliant. Or if you think about trivial case, you have a stack. You would like to build a system, CQS-based system, which is working with stack. So can you implement one method which says, okay, pop me top element of the stack? Or should you go with two functions, two methods? Peek, which will give you information about the top of the stack without altering the state of the stack, and then popping up, which will simply remove it without returning. Well, of course, you should combine those two into one. Again, this is not a dogma, this is pragmatic engineering. So yes, you can sometimes, when applicable, when it makes sense, combine seek and queue into one function, because it do make sense indeed. And then when you apply CQS to your stereotypical architecture, you get this flavor. So what we said, every interaction is either command or a query. So on the surface of our system, and here it is backend system, we are performing this separation. It will be either query, which will then return result, or this will be command, which we send to our system. And below the surface, under the surface, under the interface, we are still doing the same things. It's only that interactions with the system are either commands or queries. And then over the years, so this was first written a couple of decades ago, people were using it, it turned out to be a good idea. Then over time, this CQRS idea evolved. So Greg Young, in late 2000s, started promoting event sourcing heavily, and along with event sourcing, he came up with something called CQRS. CQRS is Command Query Responsibility Segregation. And now when you go and look at the word segregation compared to separation, separation is setting things apart. Segregation is essentially about inequality. So CQRS is applied on a method or a class level. CQRS is penetrating below the surface. So it's natural evolution where you actually split your system into two subsystems. One of them is in charge of commands, the other one is in charge of queries. And applying CQRS architectural pattern, so maybe the slide here should have been titled CQRS architectural pattern. When you apply, you get something like this. It's not about the surface anymore. So here is the surface. We penetrated our system. This division that existed on the surface was propagated all the way down to the database. So typical CQR-based system, up there you have a command. Command is accepted, and either acknowledged or not acknowledged is returned. So your command have been accepted or it was rejected for some reason. It can be any kind of transit error, or it can be authorization error or validation error. If it's accepted, your application services will manipulate domain objects and save them to a storage. Then on the query side, you have requests for some kind of a DTO or view model. This view model is not coming, usually in this architecture, is not coming from the same database anymore. You have some kind of a thin read layer or some kind of a cache where projections are computed based on the main storage. So main storage is affected by commands. You have projections or view models or read models computed. Usually you go and use some kind of specialized storage for this, and you deliver it. So as you can see, you actually have two subsystems with separated code, with separated database, and these databases are pragmatic, so to say. They are a specialized solution for specific tasks that you have. So in one case, you have a task of accepting commands and executing them. In other case, you have task of efficiently computing projections. So as a consequence of applying such architectural pattern on your project, you achieve better scalability. Reads and writes are now completely separated. You can optimize, if you think about it now as verticals, read and write. You can apply optimization patterns to either one of them without affecting the other one. So depending on the type of the system you're building, usually you have disparity between reads and writes. It's either that you're reading a lot and writing just occasionally. It could be some maybe IoT system where you're writing constantly and you need to set up some kind of alarms or aggregations or computations. But this is a good thing. You have flexibility to optimizing one or the other subsystem without affecting another one. It's also easier from the perspective of complexity management because you are making life simpler. Your code is simpler because you split it to responsibilities. And also when you think about it, you also benefit from kind of security perspective because your reads are not affecting main database anymore. You are projecting, you are computing some projections, your reads are accessing these projections. And of course, Greg Young applied this in the terms of event sourcing. And when you think about event sourcing, I don't know if you're all familiar with it, event sourcing is a concept of storing not the state, but storing events which are changing the state of a system. And then, of course, you have specialized storage. In this case, on this diagram, you have event store, which is usually a pad-only storage. So you are storing immutable events. And even when you are programming event source-based system, you will use semantics of past tense. So you will say, product added to the shopping cart. So you are stating what happened as a fact in the past. Such events are immutable. Of course, it's a pad-only storage by its nature. So using specialized data storage, usually event store produced by the same guy who invented it, or some other pragmatically chosen storage. And then, based on these events, you compute the state. If you're using domain-driven design, you will compute the state of the aggregates, or you will produce some other data model. And these projections will be served to the read side. So for example, you have stereotypical example, canonical one, you have a shopping cart, you are registering add product, remove product, change, update quantity. And then let's say you would like to see how many completed shopping carts, how many sales you have for this month. So what you will do, you will write a code which is reacting to specific events. You will run your code over the stream of events. You will compute projection, and then you will store such projection, which in this case is aggregation, into, appropriate data storage, which can be relational database. In this case, when you think about it, since you are storing events, of course, you need, for these events, you want to use most appropriate data storage. So you will use specialized data storage. And again, you are computing projections, so you can go and use something which is appropriate for such data, like relational database. Sometimes this architecture is providing way for you to have just some kind of a cache on the read side. So you can use Redis. Let's say you have high-performant system. You will use something like Redis in memory storage where you will compute the state, put it in the memory, so all your queries will be served from the memory essentially, or for some kind of specialized distributed mechanisms like Redis. In this case, what I did, I pragmatically applied CQRS. I refactored the read side where I have large pressure on. And I'm using something like Redis, which is high-performance key-value store. So you see, this segregation into two subsystems provides way for me to manipulate, to change the read side without affecting the write side. Usually, all of your business logic will be contained up there on the command side. Because commands are changing the state of the system. You're applying business rules. Your application is full of validation rules, authorization rules, business rules. All of them will be applied. Your read side is just observing the state of the system. So it's usually less complex. So I can go and use something like Redis to optimize. And you should be pragmatic. 20 years ago, there was a movement called polyglot programming, which Ted Neward came with. An idea is that you can, it's legitimate, to use multiple languages as a part of the same project. So imagine if you're building system today and you have some kind of artificial intelligence tasks. Most probably you will assign a team to use Python to implement it. And then you can go and use Java for business logic. It's completely legitimate. And even today, if you're building microservices, there's nothing preventing you, except for the mental barriers, to go and implement different microservices using different languages. In the same sense, You should always be pragmatic and look, so autopilot is switched off, of course. You should go and apply pragmatically appropriate solutions for specific problems. So let's imagine typical e-commerce project. You have search product catalog task. So you will end up using Elasticsearch, for example, to implement product search catalog, and you can use something like Postgre or MySQL or SQL Server for shopping cart. In this case, you are using 3 databases. And it may sound strange if you say, okay, I'm using 3 databases in my project. But as long as you can justify all of your choices, everything is fine. So when I'm building a project, I first have a debate with myself. I intend to use this. How can I defend my decision? And then I apply the same technique when I go and talk to my team. Have you ever heard of the term HIPPO decision making? HIPPO is highest paid person opinion. So if you have a HIPPO team, this is a problem. Because let's say I'm a team lead, I will say, okay, I made the decision that we are going to use this and I don't want to discuss it. This is obviously wrong. I should say, okay, my proposal is to use this. This is good side of this solution, technical stack. These are bad sides. Can I hear your arguments, please? I think that would be the right approach. And then if you're using something like, for example, RavenDB, you can go with a single database. So the trick here is that RavenDB contains essentially 2 databases inside. One is key value store, asset compliant one, of course. The other is indexing engine. And even though you are using a single database here, internally when you're writing, your writes will go to the key value store. When you're reading, RavenDB is forcing all your reads to go to indexing engine. So things like full table scan or full collection scan are technically impossible here. So you have guarantees of high performance, and indexes will compute your projections. So in this case, I'm using single database for CQRS, but I know what I have inside internally, so I'm not worried. I know that my queries will be served from a different specialized data persistence than my writes are using. And of course, there are various scenarios where CQRS is useful. Anyone familiar with actor model? So actors are great. This is completely different computation model, and I would be very glad if you go home today or tomorrow and take a look at actor model. I think this is the future that will come. I will just tell you that big gaming companies are using actor model. Some databases are using actor model. Actors are probably closest to original vision of object-oriented programming that Alan Kay had. Every time that you have CQRS system, you essentially driving yourself towards using asynchronous approach. If you remember, on this slide, there was something I skipped intentionally because I only now want to talk about it. This is something called eventual consistency. Of course, when you're writing to first database and you're reading from the second one, it takes some time for data to propagate from the first one to the second one. And this is called eventual consistency. So it's not immediate consistency, and this is, of course, natural consequence of using 2 databases. So you have a small delay between writing to first one and then this data that you store to the first one propagating to another one, to the second one. And when you're starting with CQRS, it may sound scary. And you're starting to contemplate, okay, my users will write to a database and then it will take, what, 5, 10, 15 milliseconds or 50 milliseconds for this data to propagate to my read database. However, it turns out that I would dare to say in over 90% of real-life business case scenarios, eventual consistency is something you can live with. Not to speak about the scenario where you have screen form for creating something in the system, user will click on a save, page will reload, he will or she will be redirected to another page. While this is happening, at the same time, eventual consistency propagation will happen. So in most of the cases, you can live with this, and even today, when I go into my e-banking or one Serbian bank, when I execute transactions, sometimes when I go on a screen, I cannot see this transaction visible, but I will not call the bank. I and millions of other people will think, okay, bank is processing this. So in reality, banks are not processing this. Banks are using eventually consistent system. In most of the cases, this is event-sourced system with CQRS in eventual consistency. So, whenever you have a read-write disparity, CQRS is a good idea. And most of applications we are building are even heavy on reads or heavy on writes. So when you're using CQRS, you will force yourself to start thinking in asynchronous manners. And when you think about high-performance systems, you will see when you start researching them and eventually building them, you will see that all of these systems are asynchronous systems. In asynchronous systems, you have a simple rule. Tell, don't ask. So you will see in high-performance systems, you send command, you get confirmation that this command has been accepted. You have no guarantees when this command will be processed. You know that it will be processed eventually. But this property of a system that you should go and tell system what to do, not to ask it right away, means that your calls will not be blocking. On the same hardware, and when you think today hardware is frightening fast, you will be able to use more of your hardware. You will actually be able to produce very high performance systems. So sometimes you might not even end up needing multiple servers. And of course, if you're using microservices, inevitably you will run into usage of CQRS. As I said, eventual consistency is something which you shouldn't be frightened of. You should be aware of it, you should tame it, you should control it, and in those rare occasions when you have problems with the eventual consistency, you will find, of course, there are ways to tame and to handle eventual consistency. And standard question from the internet, if I'm using CQRS, do I need to use event sourcing as well? No, you don't have to. We are going back to the principle. So this is principle, this is not dogma. You should be pragmatic. Of course, part of this being pragmatic part is you can use either SQL or NoSQL, what works best for you, your team, what you know best, what you think will provide services you need. And of course, sometimes you can, like in the example with Redis, you may have mental concept of the aggregates or domain model, but you don't have to create it. Sometimes, from the right model, you can create projections right away. And with event sourcing, two good things are present. With event sourcing, you are storing complete information. You are not throwing any piece of information right away. So let's imagine a simple scenario. Your users can change password, but you are not storing that information anywhere. So all of a sudden they come to you and say, okay, we need to make sure that every user change password at least once every 6 months. So what you will do in stereotypical architecture, you're expanding your data model, your persistence model to introduce time of last password change. With event sourcing, you have events, password change. So you will be able to go back, complete information is there, you will just change your code to pick up events you're interested in. So you did not lose any piece of information. And with event sourcing, you have flexibility. It's not that you will have state in the database and you will have to write migration scripts to change the database. You will simply change computation logic of computing state out of the events. You will run it, you will store it in a thin read layer. Of course, what I was doing here, I took simple architecture, I split it into 2 subsystems, I introduced 2 or even 3 or more databases. So of course, I entered some kind of technical marriage with components, with 2 subsystems, and now I'm carrying that all along. So you shouldn't be doing this if you read that. If you went on to the conference and saw event sourcing or CQRS, or if you read how Google is doing it, you should make judgment yourself. Again, autopilot is off. So what you should do, you should be pragmatic. You should be able to defend every pattern, piece of technology, database that you are introducing on the project. You should be able to defend it. If you're building simple CRUD application, there's simply no need to introduce something like this. So beware of cargo cults. Make informed decisions with full conscience. So, long-awaited answer to a question why developers actually love changes. So imagine a world where there are no change requests to the software. Over the decades, we would be building everything, we would build everything, and that's it. Everything have been built, no changes requested, we would lose our jobs. So we love changes because this is what keeps us busy. This is how we earn money, by changing software that we built. Go and dig up some books like this, Bertrand Meyer from 1987. 1,300 pages, you read it, you essentially, if you comprehend it, you know everything. If you need to read just one book, that would be the book. And essentially, instead of reading 10 books every year, maybe locate 10 books that you can go and reread every single year because they contain wisdom. Sith deals in absolute. Don't be a Sith. Don't use mental terms like always, never. Make decisions without using autopilot, without driving on autopilot, and make sure that every single project that you're building has appropriate, and this usually means different structure, different architecture. No 2 projects are the same, then why they should have the same architecture, same patterns applied. So finally, how many databases you need on a project? Infamous answer made famous by consultants is it depends. It depends on the actual project that you are building. So be pragmatic, use as many databases as you need. Sometimes you won't need a single one. My friend is these days building API for serving information about the Lego bricks. So he has CSV database in the files. He will read it in the memory and he will serve API responses from the memory. So in this case, my friend does not need a single database. Thank you. There are no questions. So either this is the worst talk ever or the best ever. Anyway, thank you and happy coding.